All right, chapter 19, we're going to jump into that bad, scary word of chemistry called thermodynamics, which isn't all that scary. It's actually a fairly simple concept. It can just be complicated. So it's simple and complicated at the same time, if that's it's possible. So what we're going to do is we're going to go through some terms that deal with thermodynamics. Now, we have covered some ideas on thermodynamics already. We've talked about energy and enthalpy, and in fact, we've talked a little bit about entropy, which is going to be our main focus here for 19.1. You will recall from Chapter 5 that energy cannot be created or destroyed. That's a law, right, as we've talked about. Therefore, the total energy in the universe is constant. However, energy can be transferred from one form to another, from the systems to the environment, or from the systems to the surroundings, and back and forth. Now, what we're going to talk about in 19.1 in general is spontaneous processes and entropy. So we're going to focus on spontaneous processes. Spontaneous processes are those that occur without any outside intervention. So for example, we have two gases, one gas in A, one gas in B. I pull the divider here and the gases are randomly going to mix. That's a spontaneous process. A nail getting rusted when it gets wet is a spontaneous process. If we go in the reverse direction is what we call a non-spontaneous process. Processes that are spontaneous at one temperature may be non-spontaneous at another. For example, ice melting. Ice melting is very spontaneous when the temperature is greater than 0 degrees Celsius. However, if it's less than 0 degrees Celsius, that would be a non-spontaneous process. In a reversible process, the system changes in such a way that the system and surroundings can be put back in their original states by exactly reversing the process. So if you can reverse the process, you can return back to the original state. Irreversible processes cannot be undone by exactly reversing the change. So it's possible, what that's saying is it's possible that a non-spontaneous process cannot be exactly reversed. Spontaneous processes are irreversible. That means they cannot be undone without adding some work into the system. So that is spontaneous process. Next up for thermodynamics, we're going to talk about entropy. We've talked about entropy before. Entropy is the amount of disorder or chaos in a system. What we have not talked about is particular equations for entropy. Entropy could be equal to Q divided by T. So it's the ratio of heat delivered at the temperature it's given. So Q, heat, joules, divided by T, Kelvin. Entropy, as we've talked about, is the measurement of randomness in the universe. Like total energy, E, and enthalpy, H, entropy is a state function, so it depends what type of matter water is. The entropy for water as a solid, liquid, and gas is going to be different. That is the idea of a state function. So if we wanted to figure out the entropy of a system, change in S is equal to S final minus S initial. For a process occurring at a constant temperature, our equation for entropy is Q divided by T. Now, what happens is the second law of thermodynamics is going to tell us that the entropy of the universe increases for spontaneous processes, and the entropy of the universe does not change for reversible processes, which would mean that the entropy of the universe is always increasing. Or, if we wanted to put that into an equation, the change in entropy for the universe for irreversible processes is greater than 0. Remember, an irreversible process is another one for spontaneous. All spontaneous processes increase the entropy of the universe, therefore the entropy of the universe is consistently increasing. Now, what we can do is we can take a look at entropy on a molecular level. So, molecules exhibit several types of motion. Right? And this motion is all creating entropy because we're talking about disorder. So, translational, the movement of the entire molecule from one place to another. Vibrational, periodic motions of atoms within the molecule. And rotational, the rotation of a molecule about its axis. So we have translational, vibrational, and rotational. Now, what Ludwig Boltzmann did is he took a picture of kind of a microstate sampling of a thermodynamic system. So he tried to take a snapshot of what molecules would look like if we had these translational, vibrational, and rotational motions all at one time. He came up with a specific number of microstates W and came up with an equation for entropy at the microstate level, which we're not going to focus too much on. Now, one thing I do want to focus on, though, is entropy in physical states. Entropy increases with the freedom of motion of molecules. So if you think about the freedom of motion of molecules, a gas, the molecules are spread out the most, so that's the highest entropy. Whereas liquids, they're kind of spread out, lower entropy, and solids, they're the closest together, the lowest entropy. So the entropy of a gas is greater than the entropy of a liquid, which is therefore greater than the entropy of a solid. Anytime we go through a phase change, we're going to have an increase or decrease in entropy. Generally, when we dissolve something, entropy is going to increase. If we go from a phase change, where we go from a solid or liquid to a gas, our entropy will increase. If we go from a solid to a liquid, our entropy will increase. If we increase the number of gas molecules, our entropy will increase. If we increase our total number of moles, the entropy will increase. So just all things that can increase entropy. When we continue to talk about thermodynamics, the third law of thermodynamics is essentially this: absolute zero cannot be achieved. Why cannot it be achieved? Because if absolute zero existed, the entropy of the universe would be zero, and that would be bad. That would mean there would be no randomness or chaos in the universe, and that simply cannot happen. So if our temperature was 0 Kelvin, our entropy would be 0. A couple things to wrap up on entropy. Here are the molar entropy values of substances. Entropies tend to increase with increasing molar mass. So you can see that the higher the mass, typically the higher the entropy. Also, something that increases entropy is larger and more complex molecules have greater entropies in comparison to smaller molecules. And I think that is kind of where I want to stop, is right there when we talk about entropy changes. Last thing we want to focus on is entropy increases with higher molecular weight and larger molecules. If we want to figure out the total entropy change in a system, the change in S is equal to the number of moles of product times the entropy minus the number of moles of reactants times its entropy. And we'll do a couple of practice equations on class where we're talking about the change in entropy in a system. But that concludes section 19.1, entropy.